Okay, I'm going to take a few minutes here and go through 4.2 Quick Check. And the idea is that in the class, we didn't spend a lot of time going over all the answers on here because we wanted to be able to get into the lab. So we're going to be looking at dissolving substances, but especially when we go back and look at concentrations, which is, how much solute we have for the solution. Specifically, we're going to do that with molarity, and we'll use the molarity formula and talk about making a solution. And we also want to talk about using the dilution formula for making solutions. And for this, we're going to be using a volumetric flask, and here's a very nice picture of one right here. So the first question here was saying, let's say we had 3 solutions, and we're going to put a certain amount of solute into a certain amount of liquid in order to make a solution. Now notice we don't say 4.5 grams of solute in 400 milliliters of water, because the solute is going to take room as well, so you wouldn't end up with 400 milliliters of solution. We say we're going to put that much solute in enough water to make that much solution. Now, I would like to start here with B and C because we have 800 milliliters in both cases. Okay, in this case we have 450, 2.25 grams of solute. So we're trying to figure out the least to most concentrated solution. So we can see if I had twice as much solute in the same volume, that B would be more concentrated than C would be. Okay, so far so good. Now the A and B both have the same amount of solute, but they have different amounts of the solution total. So if we tried to put the same amount of solute in half as much solution, then you can see that that is going to be very concentrated. So if we're trying to go least concentrated to most concentrated, I say the first thing we get is C, and then B would be more concentrated than C, and A would be more concentrated than B. And so we're going to end up with solutions down here. So I saw a picture on the internet. Here's a solution. Here's the same volume of solution like B and C, but B has twice as much solute in it. And then we have A over here, which is the same amount of solute as B, only it's concentrated into a smaller volume. So we can see that C would be less concentrated than B. B is less than A, so the answer is C, B, and A. Okay, another problem has to do with molarity. Now for this kind of a problem, we're thinking that the best way to do this is IESA. And as you know, that means write down your information. Okay, then write down your equation. Then substitute into your equation, and then get the answer. And that way it makes it very easy to follow what your situation is. Now, for a situation where molarity, we can use the molarity formula, which is molarity equals the number of moles divided by the volume. Or we can also kind of think back here to a thing we call the molarity triangle, which is exactly the same thing, molarity and moles and liters. And if we wanted, like this one here, it says, what is the volume? So if we don't look at volume for a second, then we can say, well, what are the other two numbers? We need moles over molarity. So here we get our formula that the volume is equal to the number of moles divided by the molarity. Now that's the same thing as just solving for V right here, just if you have better algebra skills. So first step is to take the problem and find out, do we know the molarity, do we know the number of moles, do we know the volume? And in this problem we have the number of moles, so that's easy, and I've written down the molarity, so that's easy, and so we're looking for the volume. Now I have my equation, and I like to, some people like to substitute into this problem because you know the molarity and you know the moles, so you could just solve for V. But I do find that a lot of times students will get the wrong answer if they do it this way, because volume is in the denominator, and they end up with the inverse of the answer rather than the answer. But if you're very careful, this works fine. So I like my equation. I substitute my numbers into my equation, and I get 0.500 liters, I'm watching my significant figures, as my final answer. So what's volume? If I had 0.15 moles of HBr, my solute, and I wanted to make a 0.3 molar solution, then I could put that 0.15 moles into 0.300 liters of solution, put enough water to make 0.3, I'm sorry, I said that wrong, divide by the molarity, and I would find out that I could make a 0.5 liters of solution. Now, second problem down here, how many grams of MgBr2 are needed to prepare 200 milliliters of a 0.8 molar solution? So again, here's my same variables. So I got my molarity, and I was given in the problem. And my volume, that was given, but I changed it to liters because molarity is done in liters, so you have to be working in liters. And then the only variable that I don't know is my moles. So that's what I'm going to solve for. And then later we have to do another step where we change moles back to grams. So I want the moles. So I could say moles, that's what I'm looking for, is going to be molarity times volume. So that's my equation. So number of moles is molarity times volume. I substitute in what I know, 0.8 molar and 0.2 liters, and I get a value here, 0.160 moles of MgBr2. Now, that's not my answer, because my answer I want is the grams of MgBr2, because if I'm going to go make a solution, I really need to know how many grams. I can't measure out moles of MgBr2. Okay, I'm going to jump way to the bottom of the page, and here's where I went back and used my periodic table. I looked up magnesium, 24.305. The mass of bromine was 79.904. It's MgBr2, so I needed 2 bromines. Put those together, and I got this value, 184.113 grams per mole. So I need that conversion factor. And I go back to here, and I do my step. Here's my moles, multiply by my conversion factor, so moles drop out, and I have 0.160 times 184.1 gives me a value of 29.5 grams. So in order to make my solution, I would need to measure out 29.5 grams of magnesium bromide. Now the next question is saying, well, how do you prepare that same problem before, 200 milliliters of 0.8 molar magnesium bromide solution? So we would need to find ourselves a volumetric flask, and it has to be specifically a 200 milliliter volumetric flask, and they come in all different sizes. So we get our flask. We need a balance so we can measure out for ourselves our 29.5 grams of the solute, magnesium bromide, that we calculated. And we're going to need distilled water. We never make solutions with tap water. We always use distilled water. Now, let's go back to here. What are the steps? So the steps would be, we're going to fill this up about halfway. Okay, about 100 milliliters, and we don't measure that, we just eyeball it. So just some water, distilled water, into your volumetric flask. We add our 29.5 grams of solute into the flask, and then we're going to swirl it around until that solute will dissolve in the solution. So we're going to swirl until the solute dissolves. Then we're going to add some more water up to the line. Now you can't see it very well in this picture. You can see it right better there. Is on every flask there's a little line that's done by hand for the volume that it says on the front of the volumetric flask. So there would be a line for 200 milliliters. So what you're going to do is to fill up with distilled water up to that line. Then you're going to put a top on the flask and turn it over a couple times to get it all mixed. And when you can't see any more Schlieren, remember the idea is that, once you have water and you have your solution, your firstly mixed solution, they're going to be different densities. So when you mix it together, you'll see little squiggly lines called Schlieren. And then, let me go ahead and write that word. And then what happens is that when you don't see the Schlieren, everything is mixed, then go back and double check that water level again. Sometimes that changes just a little bit after you stir. And when you're done, that's the directions on how to make your solution. Now the last problem on here was about dilutions. Now dilutions is if you start with a concentrated solution, then you can dilute it to whichever volume you'd like. Now that's very common with acids, because what we do is we buy them as concentrated acids. This one here we have labeled 9 molar for this problem. I think that the hydrochloric acid we buy is usually more concentrated even than that. We usually, in our personal lab, we keep 3 molar available, and we can make other solutions with that. So how many milliliters of a 9 molar stock solution of hydrochloric acid are needed to prepare 500 milliliters of 0.3 molar solution that we might need for a lab? Now, we learned before from our triangle, and that is that the number of moles is equal to the volume times the molarity. Now, we're going to use that idea because if we had a solution, the number of moles of solute in our concentrated solution are equal to the number of moles of solute in our dilute solution. Okay, it's going to be spread out a little bit more. So the moles equal the moles, so therefore the volume times the molarity equals the volume times the molarity. And we're going to use that idea to calculate our volume of our solution. Well, what happens here is we have volume and we have molarity, we have a second volume, we have a second molarity. Whoops. I'm sorry, I goofed that up a couple times. Okay, so what happens is we put in the 4 values that we have. We know we have a 9 molar solution. We want a 0.3 molar solution. And looking at the problem carefully, that 0.3 molar solution, that's the number that goes with the 500 milliliters. So you have to figure out which volume. You're going to be given 3 values in a problem. Figure out which 2 volumes go together. And in this case, this volume and this molarity go together. So we just substitute in. So we say that if we had a 9 molar stock solution, what volume do we need in order to get 500 milliliters of 0.3 molar solution? And then we just solve for x. Now notice in this case that x, the volume, does not have to be in liters. As long as these 2 units match, they're going to cancel out of the equation anyway. So, the molarity has to be in molar, but the volume could be liters or it could be milliliters. It works out fine. So our answer when we're all done, my calculator says 16.666 repeating milliliters, which rounding off to 2 significant figures, I'm going to call that 17 milliliters. So if we had 17 milliliters of the concentrated 9 molar solution, we could dilute it up to 500 milliliters, and then the concentration would be 0.3 molar. And that's how we do that kind of problem.